Okay, here we are giving this a shot today. I tried using the whiteboard yesterday and recording on my computer, and it was just like a disaster and I couldn't upload it. So this is on my phone. It's not ideal. I think maybe you can watch it individually, and then at the end I've given you a problem to do with whiteboards together. Now let me just say that we are ahead. We are February 27th last year is when I started Torque. So you guys have plenty of time to get done with everything and do well on the AP exam. Do not let the fact that you don't have a teacher be an excuse, all right? I expect everybody to do well. And even if you don't end up passing the AP exam, most of you want to go into science or engineering, so this is going to be great when you get to college and somebody else has never had any hard torque problems and you've suffered through some of these, so keep that in mind. Okay, so we're going to talk about torque today. We talked a little yesterday, but I don't know how much you heard me. So torque is rotationally the equivalent to force, and force would be linear. Torque would be rotationally. So the same ideas you use with force, you use with torque. Like for example, forces that are unbalanced cause linear accelerations. If you have an unbalanced torque, you're going to have an angular acceleration, which just means you're rotating, you're spinning, okay? But not really. You can spin at a constant angular velocity and your torques would be balanced out. So again, a torque causes an angular acceleration. That means you're spinning, but you're speeding up as you spin. That would be accelerating, all right? So I showed you yesterday that the formula for torque is force has to be perpendicular to some kind of a distance. I'll talk about that a little bit more in a second. And of course, force equals MA for forces. Newtons are the units for force and Newton meters are the units for torque. So there's a couple ideas here that are important. If you push with a force that goes to the center of mass of an object, it's not going to rotate. So I got a little seesaw here. If I put a little kid or a box or something on the middle of the seesaw, that force goes right through the center of the object. The seesaw is not going to spin, obviously. If I put a box on an edge of a seesaw, on the other hand, now all of a sudden I have a force coming here that does not go through the center of mass of the object, and this is going to rotate, okay? The point about which rotation happens is called the fulcrum. So this spot right here that goes through the center of mass, in this case, it doesn't always have to, but this is called the fulcrum, all right? Okay, torques are vectors. So this is a real important idea. By convention, they decided that counterclockwise torques, anything that causes something to spin counterclockwise would be positive, and anything that causes an object to spin clockwise would be a negative torque. So let me just say, I don't know if I said this yesterday with you all, but if you make your own convention and you forget this, you just forget it and you make clockwise positive or something and you stay with that the whole problem, you'll always get the right answer. So just if you don't remember this, just be consistent and define it yourself. Okay, if an object is not angularly accelerating, then all the torques have to add up to 0. In other words, all the clockwise torques and all the counterclockwise, the positives and the negatives, have to add up to be 0. If they don't add up to be 0, then I expect to see the object angularly accelerating. All right? Okay, so here's a simple little problem. We have a meter stick. My fulcrum's in the middle at 50 centimeters. I have a 2 Newton weight on one end. What would balance out at the 75 centimeter spot? What kind of a weight would I put there in order to balance out with the 2 Newton? Okay, I'll kind of set it up, but I don't have my calculator with me, so I won't do the math. Okay, so to do a torque problem, first of all, let's identify the fulcrum. It's right here in the middle. So I'm going to measure all my distances from the fulcrum. That's important. And they always have to be perpendicular to the force. So the first object, first of all, the meter stick itself does not have any torque because I'm balancing it at its center of mass. So if I took all these weights off, it wouldn't rotate. So luckily for this problem, I don't have to take the weight of the meter stick into account. Definitely we'll be getting into some harder torque problems, and they won't balance things at the center of mass. The fulcrum won't be there, and then you'll have to take the mass of the object into account. But here we don't have to. Okay, so how many things are making torques here? Well, hopefully you can see there's 2. This one here will cause it to go counterclockwise, so that's going to be a positive torque. And this one here is going to cause it to rotate clockwise, so that's going to be a negative torque. So if this thing is going to be in equilibrium and not spin, these two have to equal. So I'm going to take my weight here, and the force that it causes, of course, is due to gravity, right? So I'm just going to draw an arrow down. That's the force of it, and I'm going to show you on the next page, but the way I solve these, I draw a really long line in both directions that represents the force. And the distance is always the shortest distance from this line to the fulcrum. Well, in this case, of course, it's just this distance right here. So my torque caused by this one, the force is going to be 2 newtons. And the distance is going to be a half a meter. Okay? That has to equal the torque caused by this one. This one, I don't know his force, so I'm going to put a question mark there. And his distance is the distance from 75 to the fulcrum, which is going to be 25 centimeters, which is 0.25 meters. And then I would just solve this problem. 2 minus 5 is 10, whatever, and solve for t. Okay, that's how you do a problem. Like, that's a simple problem. You will not have a simple problem like that on the AP exam, but that's just a simple one. Pause that and give yourself another one if you need to try that. Okay, let's jump into a more complicated problem. Okay, here we have a beam. This is a beam. It's hinged to a wall with some kind of movable hingey thing here. And this is a chain that has some tension in it. And there's a weight hanging here halfway through. Okay, the weight's hanging halfway down. They give you that the beam is 200 kilograms, this beam here. The weight is 50 kilograms. The length of the beam is 4 meters, and this angle here, I didn't write it in, is 45 degrees, okay? And what they want to know, 45 degrees, what they want to know is what is the tension in the wire. This would be more the kind of problem you'd have in mechanics. All right, so here's the steps. You might want to write these down. First of all, pick a logical fulcrum. Well, I hope you can see that in this case, the logical fulcrum is probably already given to us. It's this hingey point. If the wire or whatever broke, this beam would rotate around that spot, okay? Figure out how many things are causing torques. So how many things are causing rotation about this point? Well, the beam itself, if I didn't have the chain or the weight there, the beam itself would fall and rotate. So the beam causes a torque. And if you think about it, if the beam was by itself and it fell, it would cause a clockwise torque. So that's going to be a negative torque. The weight causes a torque, and it is also pulling down on the beam, so it's causing the beam to go clockwise also. And this wire here is pulling the opposite direction. So I have 1 counterclockwise torques and 2 clockwise torques. Okay? So I'm going to set my clockwise equal to my counterclockwise, or you can say the sum of the torques equals 0 and solve the problem, okay? So I have it drawn here again so we can kind of do this one together. Okay, so we're going to say, let's go ahead and do it the way I did F equal. Let's say the sum of the torques equals 0, okay? So we have the torque from the beam plus the torque from the weight plus the torque from the wire equals 0, right? Okay? Now, the way we picked a fulcrum, the fulcrum's going to be right here. This is so important. This is the part that's hard for people, that this is the way I do it, okay? So each torque has a force perpendicular to a distance plus force perpendicular to a distance plus force perpendicular to a distance equals 0. All right, here's the key. The force is the force or the weight of the object. So first of all, we're starting out with the beam, and the force of the beam is the weight of the beam. So if the mass is 200, then the weight of the beam is 2,000 newtons, right? Okay, where is the weight of the beam drawn? That's an important idea. The beam can be considered to be all acting at its center of mass. So that would be where the weight is also. So right here at the center of mass is the weight of the beam, and it pulls down, right? So I'm going to draw an arrow representing the force acting on the beam, and I'm going to draw it long in both directions. This is how I do these problems. Draw that force. It's the same straight line going in both directions. Okay, now, what is the shortest distance between this line and the fulcrum? I hope you can see that it's this right here. Boom. This is distance. This is the D for the beam. See, it's not this distance here. It's the shortest distance between how the force acts and the fulcrum. Okay, how do we find that? Well, we know that the beam is 4 meters long, so we know the height. This is 2 meters, right? So this is 2 meters, and this is 45 degrees, so you can do the math, okay? I don't have my calculator, so you could use sine or cosine, right? This would be 2 sine of 45 or 2 cosine of 45, right? 2 sine 45. That should be this distance right here. Correct? Sine of 45 equals, or cosine of 45 equals adjacent over hypotenuse. So I'll put cosine. Doesn't really matter since it's a 45-degree angle. Okay. Got it? Stop the video and convince yourselves if you need to. Okay. The second torque is caused by the weight. His force is 50 kilograms times 10 is 500 newtons. And he also has the same force line, right? Boom. So his distance is going to be exactly the same. Let's see, I think I did that and I got 1.4 meters was this little distance here. This is 2 meters and use a sine or cosine of 45. Okay? Now, that added to the torque caused by the wire. Well, we don't know the force, correct? So that's what we're looking for in the problem. And the distance, well, how does the wire act? The wire can only pull in the direction of the wire. So the force line for the wire goes this way because wires pull in the direction of wires. So what is the shortest distance now between this line here and the fulcrum? It'd be this right here, right? This right here. So now you have 2 meters as your hypotenuse and 45 and just be double, so it'd be 2.8. Okay? Equals 0. So if you do the math and I didn't make a mistake, I think I got that the tension was 1,250 newtons. Why don't you try that for yourself? Okay, the hard part about this, which is not hard at all, is finding the distance. So you take any weight or any beam that's being pulled by gravity, and it's always going to be down, and so that's going to be, and sometimes your distance is going to be above it. So that's why I like to draw it in both directions, but in this case, the fulcrum's down here, so there's your distance for your weight and for your beam, and of course, the wire pulls in this direction, and the shortest distance between the wire and the fulcrum is this distance, okay? All right, now I'm going to stop now and give you this more challenging one to do as a group on your whiteboards. Okay, so we have a beam again at a 45-degree angle, and there's a weight hanging down from it. And the whole beam and weight is being held up by the tension in this wire. The wire's at 30 degrees. The beam has a mass of 5,000 kilograms. This weight is 2,000 kilograms. And the beam's length is L. All right? You're going to find out that the length doesn't matter. It's going to cancel out in the problem. If the L bothers you, make a number up for the beam length if you want. Make it 2 newtons or something. But it's going to cancel out. So if you want to challenge yourself, keep it as L and keep everything in terms of L. All right? And in the problem, we're trying to find the tension in the wire. Okay, until later.